Welcome to today's Explainer. Today, we're doing something really fun. We are completely decoding the physics of flight. If you've ever stood at an airport window, looked out at a massive jumbo jet, and just wondered how on earth that thing actually defies gravity, well, you are in the exact right place. Okay, let's dive into this, because the real physics behind flight are absolutely fascinating, and honestly, they're kind of completely different from what most of us were taught.
So to really appreciate the science of aviation here, we first have to elevate our understanding of the monumental physical challenge that aerospace engineers are up against. We aren't just dealing with something heavy, we are dealing with immense mass and inertia. When you see an aircraft parked at a gate, you really have to stop and consider the sheer aerodynamic force required to counteract the brutal gravitational pull on that colossal amount of mass. It's a staggering mechanical engineering puzzle.
Let's anchor our discussion on one specific number, 80. A typical commercial aircraft easily tips the scales at 80 tons. That's about 160,000 pounds. To put that crazy number into perspective for a second, that is the equivalent weight of a herd of roughly a dozen fully grown elephants. From a purely mathematical standpoint, gravity is relentlessly acting on that immense mass, just pulling it straight down. So to maintain level flight, the aircraft doesn't just need a little bit of upward push. No, it has to generate an upward lift force that perfectly counteracts every single one of those 160,000 pounds, continuously, without fail.
Which brings us to the ultimate question we're answering today. How exactly does an 80-ton block of solid metal just float smoothly through the sky? The answer is definitely not magic. It's a meticulously calculated engineering reality. You see, while those massive jet engines are producing tens of thousands of pounds of thrust, they aren't actually lifting the plane themselves. The actual lift comes entirely from how the aircraft's structure interacts with the invisible fluid of our atmosphere.
But before we get into how it actually works, we need to address the elephant in the room, or what you probably learned in middle school. We call it the Great Lift Myth. For decades, a highly simplified and frankly totally incorrect explanation has been passed around science classrooms. It's basically been haunting us and essentially making our old science teachers well-intentioned liars.
Now, what's really interesting about this slide is how it breaks down that exact myth. Take a look at the equal transit myth on the left. This is the idea that because a wing's top surface is curved, the air traveling over the top has a longer path than the flatter bottom. So, the myth states that the air on top must speed up to quote-unquote catch up with the air on the bottom so they arrive at the back edge at the exact same time. Sounds perfectly elegant, right? Well, look at the reality on the right. Physics tells us this catch-up rule is entirely false. Air moving over the top simply does not care about arriving at the trailing edge at the exact same time as the air underneath.
So, if the equal transit theory is completely out the window, what is actually holding up our 80-ton jet? Well, real flight is actually a brilliant, coordinated tag-team effort of two core physical laws. Let's break down the two forces that actually matter when it comes to generating that massive amount of lift.
The first force comes from Sir Isaac Newton, specifically Newton's third law, which famously tells us that every action has an equal and opposite reaction. When a plane flies, its wings are tilted slightly upward relative to the oncoming wind. We call this the angle of attack. As the jet hurtles forward, the underside of the wing violently strikes the air, aggressively deflecting it downward and backward. To give you a visceral sense of this, a commercial jet flying at cruising speed deflects literally thousands of pounds of air downwards every single second. Shoving all that air down creates a massive reaction force that physically shoves the heavy wing up.
Then we have the second half of our tag team, which comes from Bernoulli's principle. While the catch-up myth is fake, the curve or the camber of the top of the wing absolutely does matter. It essentially acts like a giant funnel. It forces the air to accelerate, stretching it out and violently dropping the air pressure. Meanwhile, the air moving along the flatter underside is moving slower, keeping the pressure down there relatively higher. So what you get is a high-pressure zone acting as a dense floor pushing up from below, and a low-pressure void essentially acting as a giant vacuum pulling aggressively from above.
So, the crucial point is that lift is never just one thing in isolation. It is a perfect tag team. The air splits at the leading edge. The curved camber on top alters the air pressure, thanks to Bernoulli, while the angled tilt of the whole wing physically deflects air downwards, thanks to Newton. By working together simultaneously, these two physical forces generate enough combined upward thrust to conquer the relentless pull of gravity on those 80 tons of metal.
To really cement this in our minds, let's think about how aerospace engineers actually map this all out.
They rely on something called computational fluid dynamics, or CFD, to model these incredibly complex aerodynamics. Because when designing a wing, engineers can't just guess or rely on basic textbook formulas. They use incredibly powerful computers and high-tech wind tunnels to visualize exactly how these invisible forces interact with the metal. They rigorously test how the streams of air split at the front, how they curve, and how they physically deflect under intense real-world conditions.
And this brilliantly illustrates what they see. When you look at a pressure map, the forces become undeniable. That large blue zone hovering above the wing, that's our low-pressure void created by the fast-moving air. And the red zone below is our high-pressure cushion violently pushing against the underside. You can literally see the physical pressure differential wrapping around the wing, trapping the aircraft perfectly between a pushing force and a pulling force to keep it perfectly suspended in the sky.
But, understanding cruising altitude is really only half the puzzle. This brings us to a major mechanical problem: mastering low speeds. When an airplane is taking off or landing, it is moving at just a fraction of its normal cruising speed. Less speed means less airflow, and less airflow normally means a dangerous loss of lift, which obviously would cause the plane to just drop right out of the sky. So how do engineers solve this mechanical nightmare and keep the plane flying when it's moving slowly?
The answer lies in transforming the wing itself midair. As the plane approaches the runway, it sheds speed, causing that dangerous loss of airflow we just talked about. To compensate, the pilots deploy mechanical devices. By extending flaps on the back of the wing and slats on the front, the wing's curve and surface area become absolutely massive. Actually, scratch that. It doesn't just get massive, it completely changes shape. This larger, exaggerated shape forcefully generates the extra lift needed to keep the plane safely airborne even at slow speeds. This is exactly why if you've ever had a window seat right over the wing, you can literally watch the wing unspool, expand, and completely transform outside your window during takeoff and landing.
Let's move to and see how this builds into the broader anatomy of the airplane. We've talked exclusively about wings so far, but it's super easy to look at those massive jet engines hanging underneath them and assume they're what keeps the plane up in the sky. People constantly confuse the physical concepts of thrust and lift, but in the realm of aerodynamics, they serve completely different jobs. They are distinct, yet fully cooperative forces with a very strict division of labor.
As this engineering axiom highlights, without sufficient forward speed from the engines, even a perfectly shaped wing cannot generate enough lift to fly. The jet engines simply do not lift the plane. They just hurl it horizontally forward with tremendous thrust. That relentless forward motion is what generates the massive rush of oncoming airflow. The wings then act as the ultimate converters. They take that horizontal thrust and, by manipulating the air with their precise shape and angle, they transform it entirely into vertical lift.
So, now that we've demystified exactly how an 80-ton jumbo jet smoothly conquers gravity at normal speeds, it opens the door to an even more extreme realm of physics. Once an aircraft is airborne and begins pushing its engines to the absolute limit, the rules of the game change entirely. I'll leave you with this provocative thought to chew on. What exactly happens to that perfectly mapped airflow, and what violent new shockwaves are created when an aircraft approaches or even exceeds the speed of sound? We will explore the fascinating physics of supersonic aviation next time. Thanks for joining me.